Okay, ready? Well, thank you, Art, very much for the invitation to speak.
Right.
I really greatly appreciate that. And very happy to be here today and to have the opportunity to talk to you about a new research consortium that we're working to put together here. This will be on low-frequency active seismology. And what we're trying to do is step change. So we're trying to increase our low-frequency capabilities by 2 or more octaves. And so that gets us down into the 1 hertz and maybe even a little beyond that. So I'll have an introduction, and then I'd like to go through a discussion on what is it that makes low frequency so challenging, and then discuss some of the prospective technologies that we have the opportunity to pursue, and then summarize with a few remarks. So this is the low frequency information gap concept is something that's been around for quite a while. And basically it's meant to describe those frequencies below the measured seismic response, which usually expands about 4 octaves or so in most situations. And those frequencies above where propagation velocities are inferred from velocity modeling. And so what we hope to do is adding 2 or more octaves to the seismic response measurement, and in so doing, help to fill that gap. So there's a lot of benefit that's expected to derive from capturing these new frequencies. And the literature speaks quite a bit to that, but I thought I'd go ahead and walk through one very simple example on 1D inversion problem. And so if we have this hypothetical impedance curve here in blue, which includes both a thin layer and a thick layer. And if I do a inversion on band-limited seismic data that includes 5 to 43 hertz, so I get the red curve here. And you can see with that red curve, there's very substantial errors in both thin layers and thick layers. And that can lead to poor inferences on properties like V-shell and porosity and so forth. Now if I include all the low frequencies, I get the green curve here, and you can see that's a much more accurate result on the inversion. And that could be of great value to folks who are trying to characterize and map reservoirs and make drilling and production decisions on those. So I've been working with the University of Houston and with the ExxonMobil upstream research company and several prospective sponsors on trying to put together a research consortium on low-frequency seismic technologies. So there's a substantial body of work that I did at ExxonMobil. And the idea is to bring that research work here to the university, and so that would include licensing on patents, project work, data, designs, and so forth. Also donation of project-related assets. There's a number of consultants that were involved that we'd like to be able to continue working on this, so releasing those. And in return, ExxonMobil would get member benefits to the consortium. Now, sponsors would pay a fee to join the consortium, and that money would go to advancing the research. And in return, they'd get the sponsor member benefits, which would include licensing to the research and also to the background IP. And so the idea is that we would take technologies, candidate low-frequency seismic technologies through the research stage. And so that would include theory work, small-scale experimental work, and then finally full-scale or application-scale experimental work. And we'd take that to the point to verify the validity and viability of the technology for commercial seismic applications, and also to establish specifications for its application in commercial seismic. However, that's where the research consortium itself would stop. The idea then is that in the commercialization step could be done, sponsors could take that up, or partnerships, groups of sponsors in partnership, or even a university-led GIP of some sort. But the objective of the consortium itself would be to reach that research conclusion and de-risk the technology and show the technology is viable. So that's what I wanted to say as an introduction. Now, why are low frequencies so challenging? So I want to talk about three key factors: the Earth ambient noise, seismic source strength, and far-field amplitudes and how they relate to source output. And then I want to walk through a few examples that illustrate what's happening at the low frequencies. So Earth ambient noise, unfortunately, rises very dramatically at low frequencies. And there have been a lot of studies on this. Here's some results from Berger, which is taken from the Global Seismographic Network, and a chart out of Gabrielson, who's a Navy research guy. So this is related to pressure measurements in the marine environment. And usually what these studies are trying to do is understand what the quiet Earth steady state noise floors are. And so these are the best case condition for noise in the Earth. And usually, of course, in our seismic surveys, we're probably not going to see noise this low, but we certainly probably won't see noise lower than this. So they're both plotted as acceleration noise, and in case of Gabrielson, he shows it as a function of frequency. In the case of Berger, he's showing it as a function of period. So what I did is recast that data into another graph, into properties that are a little more familiar. So Gabrielson here is represented in pressure, and Berger is represented here as a velocity, and both plotted as a function of frequency. And of course, we're kind of interested in this, the few octaves around 1 hertz or so, and you can see that these slopes are very steep. And again, this is the best case scenario for noise. And in fact, some of these slopes are getting as high as 24 dB per octave. So we have that issue, which is a very important issue to deal with. At the same time, we have very rapidly diminishing output in seismic source strength. And by way of example, let's talk about the hydraulic actuator that's common in land vibrators. So the force output of a hydraulic actuator is proportional to the inertial mass, the driven displacement of the mass, and frequency squared. So all these actuators have a maximum displacement limit, and that's usually somewhere around 10 centimeters or so. And that usually happens around 5 hertz. And once you reach that maximum displacement limit, the force output falls frequency squared. So by the time I'm 2 or 3 octaves below that displacement frequency, I've lost 1 to 2 orders of magnitude in force output. So that's a very dramatic decline. And then also, this is a figure out of Hegna and Parks. Air guns fall very rapidly at the low end. And so you can see the various air gun arrays here, and I've kind of marked where 5 hertz is, and you can see the fall off is the output's falling off very rapidly in that neighborhood. So we're dealing with that issue. And another issue that one has to deal with is the fact that far field amplitudes scale with the product of the force output of the source and the frequency. So if I want an amplitude in the far field to be the same at half the frequency, an octave down, I've got to double the force output of the source. So those 3 factors combined are working very strongly against us. in the next section, I want to show a few examples. And the first one I want to show is how those steep slopes affect our objectives of being able to measure down another 2 octaves. And then I have another couple examples I'll go through just to show how low frequencies respond, what the response from the Earth can be like. So what we're going to see out of this discussion about the steep slopes in the noise and the source power is that we're going to need orders of magnitude improvements in low frequency source output in order to achieve 2 or more octaves. Something like a doubling or a few multiples improvement is just not going to do it. So here is a coherent spectra and power spectra from an experiment done in relatively shallow water in the Gulf of Mexico about 15 years ago by ExxonMobil. These results were published by Norris and Johnson and IPTC. And what this is, I want to be clear, the coherent spectra is the coherence between independent realizations of an experiment. So it is not the coherence between adjacent traces in a gather, just to be clear. And so by repeating an experiment and looking at the coherence between those experiments, you can very accurately and cleanly identify what proportion of the power in the recorded traces is due to the source and what proportion is not due to the source, presumably the ambient noise. And so you can see the coherent spectra here, and above 6 hertz or so, a very high proportion goes from 0 to 1, very high proportion attributable to the source. And by the time you're down to 3 hertz, practically a 0% attributable to the source. And if you take that observation in combination with the power spectra, what you can do is you can discern what parts of the power spectrum I'm seeing the source, and in what parts of the power spectrum I'm seeing ambient noise. And when we do that, we can discern from this picture that in this case, in this experiment, in shallow waters of Gulf of Mexico, we were seeing slopes in the noise as high as 30 dB per octave at the low frequencies, and fall off in the source as high as 30 dB per octave the other way. And so those two combined is a massive wall, a very difficult barrier to attack. So let me just show why that's the case. So I've drawn here 2 lines at 30 dB per octave and had them intersect at 5 hertz. And so that would be sort of our point of reference would be the intersection where the signal to noise is 1. And notice here's an octave, 2.5 to 5. So that's kind of the scale of this. So if I raise the source output 6 dB, which would be a doubling of the source output, which would be a major addition in source output, what we see is we only move that interception point by 1/10 of an octave down to from 5 hertz to 4.67 hertz. And that's a long way from our objectives of being able to do 1 to 2 octaves. So that's a real wall. Now, in some cases, we might be able to work in areas where the slopes are as low as 18 dB per octave. But even in this case, if I were to raise the source output 6 dB, I only achieve 0.17 octaves. So these slopes really represent a tremendous barrier to the low end. And once again, what that means is that doubling or a few multiples is not going to do it. We're really going to need orders of magnitude improvement in the source output at the low end. Okay, so let me show another example on how a 1D layer, the response of a 1D layer at low frequencies. So one thing that we know is that low frequencies are critical to inversion for layer properties. But what we're going to see here is that a single layer has a weak response at the lowest frequencies. So here's a layer in a medium with velocity c0, the layer being velocity c1 and thickness b. And I'm just going to draw that layer in two-way travel time in order to make it easier to relate to our measurement frequencies. And so now the two-way travel time is 2b over c1. And if we just take the Fourier transform of that to see what the structure, what the content of that is, it's the rectangular function is a sinc function. And what you see is that the most important content to this structure are the low frequencies. You can see the biggest lobe here at around 0. And in fact, the frequencies with periods that are greater than the two-way travel time of the structure are the frequencies that are contributing the most. So I'm going to zoom in on that sinc function here a little bit, and now let's talk about what the actual measurement response of this structure looks like. So we have, for the top of the structure, a positive reflection coefficient, and for the bottom, a negative reflection coefficient. And assuming just the primaries, we look at the measurement response of that, and this is the magnitude of the response versus frequency. We see a lot of zeros here in the response, and the zeros out here aren't too bad of a problem because they correspond to where there's no contribution to the structure. But notice we have, at the very lowest frequencies, we have a 0 precisely in the place where you've got the largest contribution to the structure. Now, fortunately, there's a lot in here that you can still get. You know, the measurement response is still very strong in parts of this lobe. It's just as you get to the very center, and I've kind of marked off a shaded region here for periods that are greater than 4 times the two-way travel time of the layer. So that's another challenge as far as the lowest frequencies are concerned. So this is just a sequence showing how the center frequencies contribute, and I've run this for just for the example a thickness of 150 meters, a velocity of 2,400 meters per second. So in this case, this layer would have a two-way travel time of 125 milliseconds, which corresponds to a frequency of 8 hertz. And so if I only have frequencies that are greater than or equal to 8 hertz, that's what that structure looks like. If I add another octave to that, that's what it looks like now. And yet another octave down to 2 hertz. And another octave down to 1 hertz. Now at this point we're starting to get into the measurement notch, so it's going to be getting a lot harder to get this information. And then finally one more at half a hertz. So low frequency is important. However, as you get to the very lowest frequencies, they become even harder to measure because the response is weaker. But that's anecdotal. That's just for the single layer case. Now I want to end with some good news, and that is that there's a lot in the Earth that we expect to be able to see with the low frequencies that you, in fact, can't see with the higher frequencies. And so one example of this can be shown through the Wolfram problem. And here what we're going to do is show that some structures are not visible with conventional band frequencies, but can be seen with the low frequencies. So the Wolfram is named after Alfred Wolf, who published the analytical solution to the backscatter of this structure back in 1937. And what the Wolfram is, it's a transition from one velocity c0. It's a transition linear in depth from one velocity c0 to another velocity c1, which takes place over a distance b. So I've got the Wolfram drawn here, and you can barely see it, but it's a light gray dotted line pattern for a step function as well with the same amplitude there. And what I'm doing here is I've picked an example where b is 350 meters, and I'm going from 2,000 meters per second to 3,000 meters per second. And I'm going to plot the responses over here assuming a Ricker wavelet, incident Ricker wavelet. And I'm going to plot it as a function of time times the peak frequency of the Ricker, so that I can get several octaves on here conveniently. And I've also indicated with small tick marks where the beginning of the ramp is and where the end of the ramp is. And so the travel time of the ramp is always the same, but as I go to lower octave Ricker wavelets, you'll see this tick mark moving in because this is times frequency, peak frequency. So here's a 16 hertz wavelet, and you can see the step function there, barely. Looked better on my screen. But you can also, in red, see the Wolfram response, and you can see the Wolfram is practically invisible at these frequencies. If I go down an octave, the Wolfram is still very difficult to see, and you can see the tick mark has moved in here, showing the beginning and end of the ramp. I go down another octave to 4 hertz. Now I'm starting to see an expression for the Wolfram, down to 2 hertz, and then finally at 1 hertz, the Wolfram is very clear. So here's a case, unlike the single layer problem, where we're actually going to be able to see this structure much better at the low frequencies. Okay, so once again, the challenge, 3 key factors. We've got rising ambient noise at low end, we've got falling source strength, we've got weaker far field amplitudes for a given source force, we've got some things in the Earth which are harder to see at low frequencies, some things in the Earth which will be easier to see at low frequency, which is the positive going for us. And so, given those challenges, what are prospective technologies that are going to meet the key issues and allow us to achieve another 2 octaves? Remembering that, as we concluded before, we're going to need orders of magnitude improvements in the source output. And this is probably not going to be doable by adapting or upscaling existing technologies, or at least that's a presumption, but rather is going to need new ideas and major new innovations in order to achieve those kind of step changes. So when we started this project back at URC, my colleagues and I just kind of mapped out, what were the key issues in source, receiver, land, and marine environments. And as we mentioned before, for land sources, you got very low output, force output. You have the same thing in marine, but in addition, you've got a source ghost notch at low frequencies to deal with. And then on the receiver side, really the main issue is in the marine environment is with multi-component streamers where the velocity component, the complementary component to pressure, tends to be very noisy at low frequencies. You'd like that to be very clean at low frequencies if you can. So those were sort of the areas that we thought needed new innovations. And notice I just have the check mark here for the land. So there are ground motion measurements, which are actually very good to very low frequencies, and the earthquake seismology community uses that quite a bit. So we gave that one a pass because we thought, well, in principle, the technologies are out there, although there may be some adaptive work, in engineering and so forth to make it commercially interesting for the seismic industry, for the oil industry. But meanwhile, these other areas clearly needed some major new types of equipment, we thought. So we came up with these. So these identified the key issues, and then we came up with what we thought were potential technologies that addressed those key issues. So we're going to go through those one at a time, a few words on each of these. And we're going to start with the marine dipole source. The primary benefit of the marine dipole source is that it doesn't have a low frequency ghost notch, but rather its ghosting characteristic provides an amplification at low frequencies. And so what I've done here is I've drawn various ghost functions, receiver side ghost functions and source side ghost functions for conventional sources. And down here you can see sort of the frequency response, the frequency domain of the response in each ghost function. So this one's on top is always the pressure, and this one on bottom is the particle velocity. And of course, on the receiver side, we know that we got a ghost notch in pressure measurements. We have ghost amplification and particle velocity measurements. On the source side, with conventional marine sources, whose characteristic is they radiate the same thing in all directions, you have a notch at the low frequencies, whether you're looking at pressure or particle velocity. That's always notched. And so what we want and what we have with the marine dipole source, the marine dipole is a source that radiates opposite polarities in opposite directions. So what you have in this case is whether you're looking at pressure or velocity, you've got to have a ghost amplification. So if your interest is low frequencies, then ideally, at least as far as ghosting functions are concerned, you'd like to have a dipole source on the source side and a low noise particle velocity measurement on the receiver side. So that's easy to say. You know, we want a source that radiates opposite polarities in opposite directions. But what does the implementation of that look like? And are its characteristics and requirements something that is realistic for seismic applications? And so we did quite a bit of work on the theory of this and how it works. And we compared the monopole source to a dipole source. And went through, described the boundary conditions, and did the solution for the radiated wave, and so forth. And basically, the big difference is that a monopole source drives acoustic waves by volume modulation. And so by driving volume change, it puts pressure on the surrounding medium, and that pressure propagates out into the medium. Now, the dipole source, on the other hand, has no volume modulation. It's a rigid fixed volume, and it's being driven to translate up and down in the water column. And so when it's being driven up, forced up, it's compressing on the top, and it's also at the same time rarefying on the bottom, and then that's radiating out opposite polarities in opposite directions. So I won't go through the entire solution to the acoustic wave solution to the dipole source, but I do want to focus on a special case of the solution, and that is in considering the far field where Kr is very large, and considering low frequencies, which is where Ka is very small. Now this condition, meaning that A is the dimension of the source element, and K is the wave number of the propagated wave. So what we're saying here in this condition is that the source element is much smaller than the wavelength of the radiated wave field. And this is a very critical condition, because if we're interested in, say, 1 hertz in water, that's a 1,500 meter wavelength. And we can't have, if we have to have sources that are of the order of the wavelength, that's not going to be a very practical thing. So it's very critical that we can talk about reasonable size sources to generate these huge wavelengths. And what we learned from looking here, this is the solution under those conditions. So this is the far field pressure at low frequency. K again is the wave number. F sub r is the forcing on the fluid from the dipole. And then the rest of these terms here. If you a full description there is published in JSC this last June. But what we learned from this term are several important things. Number one is that a dipole source does have a low frequency far field radiation to it. Number two is that the dipole radiates opposite polarities in opposing directions, and you can see that in the cosine theta term, the theta being the angle from the axis of translation. Third is that the far field amplitude does not depend on the size, or the shape for that matter, of the dipole element, which was surprising. That was counterintuitive to us when we first started, but that's clearly what the theory is telling us. You see there's no reference to the size of the source element at all here. The only place it shows up is in the phase term up here. And however, in case number 4, the other important factor is that the far field pressure does depend directly on the forcing, the size of the forcing that the dipole is pushing on the water. So we went the next step of doing scaled experiments to verify all those aspects of the theory that we thought were going to be important. And these were scaled low-frequency experiments, and by that what I mean is that Ka is small, but we're not doing 1 hertz experiments. So in fact, these experiments were 70 hertz to 700 hertz, but the source element were typically, 8 inches, a foot, something like that. So those were, the source dimension was very small compared to the radiated wavelength. So this is just this is a photograph of one of our dipole elements. Inside the element are actuators, electromechanical actuators, which drive a translation. And this is a picture of a good portion of the seismic pond where we did the work, and one of the arrangements here. What you're seeing here are surface floats where we suspended hydrophones into the lake, and right here is where the dipole element itself is being suspended. And we actually did a full summer of experimental program on this. And what we learned from those experimental results is that it very cleanly and beautifully verified what our theory predictions were. And so this is just a figure here showing some of the data, showing clearly radiating opposite polarities. If you look at the first kick here is negative, the first kick on this side is positive. Clearly radiating opposite polarities, and also showing just generally the cosine theta pattern, radiation pattern. And we also saw the far field amplitudes that were predicted and their relationship to the forcing that the electromechanical actuators were providing in the dipole element. And also, very importantly, that this is all confirmed for dipole elements that are very small. So for example, here the fundamental frequency of this, or the data was, in this case, was 175 hertz, was the drive of the dipole source. At that frequency, we have a wavelength of 28.1 feet, but the dipole element itself is only 8 inches by 8 inches. So clearly, it's doing all this under those Ka small conditions. So that was all very good news. But the one piece of challenging news out of that was that the dipole source is going to need that strong forcing in order to radiate useful far field amplitudes at the low frequencies. And in fact, it looks like we're going to need several hundred kilonewtons of forcing at these frequencies. And this is something that's not easily achieved with the existing seismic actuator technologies that are out there. So here's a chart. This is actually out of one of the equations out of the publication, which shows the amount of forcing that's needed to generate a far field pressure of this magnitude at 1 hertz, a distance 1,500 meters away. And we believe that we're going to need amplitudes in this range in order to be useful for seismic exploration. And that's going to require forces in this range. And that's where we get the several hundred kilonewtons from. So that raises the important question was, is there a practical actuator to provide the forces that are needed to radiate these low frequencies? And that brings us to the next topic of the counter-rotating eccentric mass actuator. So this is a technology that can provide large forces at low frequencies. So going back to our picture of the hydraulic actuator and seeing that the force output is proportional to the inertial mass times the distance displacement of the mass and frequency squared. And remember that we're losing 1 to 2 orders of magnitude force output as we go 2 to 3 octaves down. And the only way you can make that up is by increasing the mass or the displacement or some combination of the two by orders of magnitude. Well, increasing the mass substantially is a very challenging proposition. Masses are already pretty big on these devices, and in order to be able to get them around, drive them on roads and things like that, you don't really want to make them a lot heavier. But one thing you can do is to increase displacement by orders of magnitude, but not with hydraulics. You can do it if you choose a different type of actuator, and that would be something like a counter-rotating eccentric mass actuator. And what you're doing here is you're taking the masses and you're rotating them about an axis of rotation. So I've got a mass out on an arm, and the total displacement then of that mass is going to be twice the radius of rotation. And then I have a second one over here, which is rotating in the opposite way, and the idea is that that cancels out all the horizontal forcing and leaves just the vertical forcing. And so it looks something like that. And you can see with the star is meant to indicate sort of the center of mass of the system, and you see that mass is going just straight up and down and vertical. And that's going to provide a force in the vertical. So then by way of example, let's say I had two masses in this system as opposed to the one mass in the hydraulic, and I had, let's say, a 1 meter radius arm for a total displacement of 2 meters as opposed to the 10 centimeter limits of hydraulics. That's going to be able to get me 40 times the force output. And so a nominal force curve for a CREM actuator can look something like this. And you see here that we're getting several hundred kilonewtons in this case, down to 1 hertz. So the idea is that one could have a device like this inside the dipole, providing the forcing and the drive for the dipole. Obviously, you would also have potential land applications for an actuator like this. And so we did a lot of small-scale CREM experiments and got very good results with those. So we proceeded on to build an experimental CREM array at a full application scale to see if this thing could actually work at the size that you need it to work. And we call this the CREM VXP. This is one of the project assets that we're wanting to move from ExxonMobil to the university so we can continue working on it. But its purpose is to test if CREM actuator, if the concept can provide the large forces at low frequencies in the manner that we need for seismic applications, and also to determine how much force and how much sweep time will be needed for commercial arrays by using it to measure and characterize Earth response signal-to-noise ratios at these frequencies. I would say right now we have an idea of what it might take, but it would be nice to be able to take it out and actually do some measurements of signal-to-noise and verify that. So this device is capable of producing 400 kilonewtons at 1 hertz, 90,000 pounds. It has a mass rotation and eccentricity controls, which are controlled independently. And so that allows you to do controlled waveform sweeps. And it can operate in the 1 to 6 hertz band. And so sort of the idea here, you can see it's a platform. It has 2 sets of counter-rotating masses for a total of 4 masses. And the idea is, you can see the axis of rotation is right up here. And what you would do to start the machine is you pull the masses up to 0 eccentricity. And once you're at 0 eccentricity, you can begin a spin. And you can spin it up. Once you spun it up to the rotational frequency that you want to start your sweep at, you slowly let the masses out, increase the eccentricity so that you begin to get the force output. And so that's how that would work. It's about 80% completed. We hope to get it here to the university and finish it and do some actual field experiments on it with it. Okay, now the other topic was the receiver side in the multi-component streamers, being able to get low noise measurements, low frequency, low noise measurements. And so here we have the what we came up with as a pressure gradient transducer concept. And the way this would benefit us is that by having a transducer that directly senses gradient, you avoid the low frequency motion noises from motion sensors that are common in multi-component streamers. So of course, the multi-component streamers are a two-component acquisition, and a lot of their motivation is to get the information that's required to do the receiver side deghosting through the wave field separation. Of course, we have a lot of experts on that in this room, leading contributors in that area. So I'm not going to talk about how you get this and how you apply it. But what I do want to talk to, and I think Jin Sang mentioned that this explicitly this morning, is that the measurements that you need for the wave field separation and deghosting are pressure and pressure gradient. So the industry is very good at doing pressure measurements, no problems there. But in fact, we don't really do local pressure gradient measurements. One of the common approaches, and what's used in multi-component streamers, is to use motion measurement as a proxy for pressure gradient. And the way that's used is you measure motion, and then using conservation of momentum, you infer pressure gradient from that motion measurement. And that should work absolutely fine as long as the acoustic wave is the only dynamics of the system. But unfortunately with streamers, there's a lot of other dynamics going on. And so if I consider the full relationship between pressure gradient and motion in Navier-Stokes equation, you could see that inferring pressure gradient from motion is much more difficult to do. And we see this becoming very problematic as you get to the lower frequencies in multi-component streamers. So what we contend is that what you really want is a transducer that would directly sense pressure gradient and is really insensitive to motion. And we hypothesized a pressure gradient transducer concept to do that from solid state principles. So how that works is, the energy band gap in semiconductor materials controls the concentration of free electrons in the conduction band and corresponding holes in the valence band. And it's known that there are some semiconductor materials out there that have energy band gaps that are sensitive to pressure. And what happens is when pressure increases in these materials, the energy band gap increases, and that reduces the free carrier concentration. So our pressure gradient transducer concept then is based on the proposition that if I have a variation in the pressure across a semiconductor material, that causes a variation in the energy band gap and corresponding variation in the free carrier concentration. And then that variation can be exploited for a transducer effect. So the hypothesis is stated here in two parts. One we just said, a variation in pressure causes a variation in the energy band gap and corresponding variation in the free carrier concentration. And then part B, an electrical response proportional to the gradient in free carrier concentration can be generated and measured. And we actually are getting close, we're near completion of an experimental program that validates that proposition. And in fact, as far as part A is concerned, this has been verified and those results are published. So we have confirmed the relationship between pressure and free charge carrier concentration. And the way we did that is we built a structure here of indium antimonide and a PZT to drive a standing wave pattern single wavelength standing wave pattern in the INSB. And it turns out that you can use a laser diagnostic to directly measure the free charge carrier concentration. And so we used that and measured at numerous points along the length of the INSB. And from the measurement of the carrier concentration, working back through the band gap and so forth, inferred what the pressure in the material is. And that's plotted here with the blue dots. And you can see a double lobe amplitude here, just as you would expect in a standing wave, single wavelength standing wave pattern. And then in addition, what's shown here is the relative phase, and they are 180 degrees out of phase. So we're getting the right dynamics in the measurement, and we're getting the right amplitudes, which agree with what the amplitudes mechanically that you expect out of this system. So the next step is part B, and that's showing that you can in fact get an electrical response proportional to the gradient in free carrier concentration. And so for that portion of the experiment, we've modified this structure and included some fused silica in the stack. And the reason we're doing that is when we generate a pressure gradient in this material, we really want it to be in only one direction at a time, because if you have it in both directions, you're going to get currents in both directions and they're going to cancel each other out. So we just want to generate a current in one direction. And so we just have this much INSB. In addition, you need to apply a strong magnetic field. And this is, we're chasing a diamagnetic current effect here. You need to apply a strong magnetic field, and then you need electrical contacts, and you need, as it turns out, a very low impedance measurement capability. And so we developed an active measurement capability. And so the idea is that you apply the magnetic field, you excite the structure, you get pressure gradients, as a function of time, changing direction. That generates a current, a diamagnetic current off the device, which we'll measure. And if it all works out, what we'll see is we're getting currents that are proportional to the pressure gradient. And there we have a transducer for pressure gradient. Of course, the next steps, so that's just verifying the fundamental theory, and then the next steps would be to see if we can actually see seismic scale pressure gradients. So those are those three technologies. So let me just summarize. So we have these technologies which we started to pursue at ExxonMobil, and they're in various stages of development, but they each answer an important part of the challenge for the low frequency acquisition. So we have the marine dipole source in the marine environment, which reverses the low frequency source ghost notch to source amplification. We're pretty much through the theory and small scale experiment work on that, and really ready to go to the next stage, which would be to build an experimental prototype to demonstrate far field amplitudes actually down at 1 hertz and 2 hertz. This one's further along in that we did all the early research on this. We did the small scale experiments, and we're actually now nearly complete with a full application scale experimental prototype. And once it's completed, we'll characterize that and also take it out and get some earth response measurements at 1 hertz and 2 hertz and develop specifications on exactly what's needed to do acquisition at these frequencies. And finally, the pressure gradient transducer, which directly senses pressure gradient and avoids motion noise at low frequencies in multi-component streamers, is still very much in the early stages, laboratory. We're still confirming the transducer effect actually exists, and then you need to go through steps to see that it would actually be useful at the seismic scale. So once again, we're trying to put together the consortium that allow us to continue this work. And the idea is to take this work, or really any If a better proposition or a better concept comes along, take that concept, take it through to the end of the research stage, and have it ready for commercialization, for someone to take on the commercialization challenge. So here I'll just leave you with, here's my contact information. We are talking to prospective sponsors, so if anyone would like to see more about this material, we've been going around and we've had some detailed discussions with several prospective companies. And also here is a list of recent publications, 2015 and later, on this work. So that's what I have, and thank you very much.